Now we know from previous work that we've done all levels of mathematics that when we take a measurement, when we do a calculation, when we do some sort of equation involving a number that continues on with a decimal or needs to be rounded to a certain point, essentially what we're doing is approximating that number. So for example, if you imagine pi, we round it to 2 decimal places, it's 3.14. But we know that pi continues on for trillions and trillions of decimal places beyond that. So what we are essentially doing is approximating pi to that 3.14. Now, when it comes to certain types of data, using rounding and using this approximate value that we have gives a general fuzziness to the data and can actually introduce an error that makes the data and calculations we can do with it unfathomable, something that we can't rely on, and what's called ill-conditioned. Now, as I've said, when we make a measurement and it's made using rounding, the resultant data takes on some fuzziness. So let's say if I said to you x was equal to 51 to the nearest whole number. X could be anywhere between 50.5 up to 51.5. So it could be anywhere in that gap, not including the 51.5. Obviously that would round up to 52. Now this is often quoted as 51 plus or minus 0.5. This 0.5 here, this is what's called the absolute value in measurement. It indicates where the absolute highest and lowest values that we can use lie. Now, a size of error that can occur when we use this sort of rounding is often quoted as a percentage of the associated measurement. So, for example, an error of 0.5 in 51 represents about 1% error in measurement. This percentage error is a better way of judging just how bad this error is in relation to the data and the information we have. If the error, the percentage error, is high, this essentially invalidates what we've done because it introduces such a high percentage error and such a high error within the system that the data essentially becomes invalid. Even though it might not look like a great amount, the fact that we've got a high percentage of error brings that into play. So let's imagine similarly we take y equal to 50, again to the nearest whole number. That means that we can have y lying anywhere between 49.5 and 50.5, non-inclusive of the 50.5 itself. So let's imagine then I take these values for x and y, so x is 51, y is 50, and I add them together. With those rounding values, this should be 101. But because of this, because of the fact we've rounded them, it could be as low as 100, so the 49.5 plus the 50.5, or as high as 102, as high as the sum of the two highest values. So what that means is actually 100 is less than or equal to x plus y, which is less than 102. So x plus y equals 101 plus or minus 1. So what that means is in this calculation we have an error of about 1%, which is acceptable in quite a lot of situations. But let's imagine we look at it from another perspective and we look at the value for x minus y. What would happen then? Well, if we look at x minus y, if we take the rounded values, would equal 1. What this means is that it could be as low as 50.5. Again, because we're using the rounded values, 50.5 take away 50.5, which is 0. And as high as 51.5 take away the 49.5, which is 2. So it falls in that gap. Now what that means is 0 is less than or equal to x minus y, which is less than 2. Or in this case, x minus y is equal to 1 plus or minus 1. Now this absolute error then is 100% of that original part, because 1 is 100% of 1. Now what that means is this subtraction has no meaning because it's got such a high percentage error associated with it. Now, it doesn't seem much in terms of value, but if you were to tell somebody the percentage error within their system was 100% error, that would then mean that you couldn't really apply it. It wouldn't be applicable and accepted in that scenario, dependent upon what you want to do. Now this allows an unacceptable amount of error to build up, and what that means is our system becomes ill-conditioned. And particularly in real life situations, we try and avoid this. We need accuracy in a lot of situations. Let's imagine we take this example that we've got here, with the numbers we've got in the information, and let's apply it to a scenario where we have a metal rod. Now the metal rod measures 51 millimeters to the nearest millimeter. What we do is we take this metal rod after we've heated it and cool it down. As we cool it down, it contracts. What then occurs is that the length is measured again and we get 50 millimeters. Again to the nearest millimeter. So we then ask ourselves, how much is it contracted by? Well, in order to do that, we'd have to say 51 take away x is now 50. Because it's the original amount, take away something to give me the new contracted amount. Now, obviously, we rejig it, x is equal to 51 minus 50, which is equal to 1. But this is exactly the same situation as here. This is that exact same situation as is there. So what that means is x is technically 1 plus or minus 1. And that introduces a 100% error within our system. What that means is no useful result can be gained from this equation. We can't really get a decent result using this equation here because of the fact that we're using these rounded values in our calculation. And it introduces such a high percentage error, it makes our system ill-conditioned. Now it's a lot of information here to throw at you, but what we're able to do is actually use this and represent our system using matrices and equations of systems of equations. And then when we do this, we can use these systems of equations to get values for x and y. And if we were to make a tiny change to something within that system, and this resulted in a massive overall change to our final solution, what we'd then be able to say is the system's ill-conditioned because of the fact that that tiny change makes such a big overall difference to our answer. So this is what we're looking for in order to demonstrate an ill-conditioned system of equations. Let's look at this system of equations that we've set up here. So I've got x plus 0.99y equals 1.99, and I've got 0.99x plus 0.98y equals 1.97. Now let's look at solving this system of equations. First step is, as usual, we stick it in an augmented matrix. So we've got 1, 0.99, 1.99. We've then got 0.99 in the x there, 0.98 in the column representing y there, and 1.97 in our solution representation column. What I'm then going to do is to start to solve it using elementary row operations. Well, I only have to do one because I want this value to be 0. What I'm going to do then is do row 2, take away 0.99 of row 1. That'll eliminate this value and allow me to read off my solutions. So what that'll tell me is that I've got a 1, 0.99, 1.99 in the top, and my bottom row will give me a 0 there, negative 0.0001, and then negative 0.0001 there. So what I can do from that is I can look at this and read off that y is equal to 1 and x is equal to 1. So that's the solution to this system of equations as is here. Let's imagine I'll take that exact same system of equations and I will make a tiny change to it. Let's imagine I change it to be x plus 0.99y equals 2.00. And I'm going to then take everything else as being the exact same. So I've got 0.99x plus 0.98y equals 1.97. So I've just made that tiniest. The changes there. I've added 0.01 to my final solution in that first equation. Now what I'm going to do is solve it the exact same way. So I'm going to start by taking it and putting it into an augmented matrix. So that augmented matrix looks like 1, 0.99, 2.00, 0.99, 0.98, and 1.97. And I'm going to try and solve it the exact same way. So I'm going to do the exact same operation, do row 2 take away 0.99 row 1. What that's going to do this time is give me a system that looks 1, 0.99, 2.00. I'm then going to have 0 here, negative 0.0001, and this time I'm going to get negative 0.01 in this case. So what that means is if I look at this system here, I'm going to get negative 0.0001y equals negative 0.01. So this actually gives me a solution where y is equal to 100. And if I then take the y equal to 100 into here and substitute it into this solution here, what I'll end up getting is that x plus 99 equals 2, so x is equal to negative 97. So what I've done is I have literally added 0.01 into the system as a solution here for this first equation, and I've taken my solution, which was x is 1, y is 1, and I now have a solution where x is negative 97 and y is 100. So that's all I've done. Now that makes it an ill-conditioned system. Geometrically, you could almost think of this as taking these two here and using them to represent a pair of lines with a tiny, tiny angle between them. Alright, and for this system of equations, I've got one solution, which essentially is a line that goes between the two of them, where I get one answer there. What I've then done is taken it, and because I've got a solution here, none of my gradients or anything have changed. All I've done is taken this line and made it a parallel line somewhere further up the system. So let's say here, but what has happened is because of the distance I've moved, even though it's a tiny amount because of that, the answers have actually become massively different from one another. They've spread out even more to what we would have had to begin with. So the error that it introduces into our system gets greater and greater, which means the system becomes more and more ill-conditioned when I'm working it through. We have to make sure we follow this idea that using rounded answers can introduce this error. It can introduce a high percentage error into whatever system we are representing. And this error, when it comes into play in real life scenarios, so in the previous example that I showed you, this can have a massive effect on the overall solution and the overall result that we want from our system. Bear it in mind that this here is the property of an ill-conditioned system, where we make one tiny change within our system and it has a massive overall effect on the solutions to the system and takes it greatly away from what they had as a previous answer. So in this one we've gone from 1, 1 to negative 97, 100. That's a massive difference for a tiny introduction of 0.01 as a part of a solution to one of our equations.